All right, so today's topic is hashing for blockchains and cryptocurrencies. So cryptographic hash functions are really, really important. So first we will see foundations of it and why they are secure or how they are secure, which ones are broken and which are secure to use today in 2023. So let's remember the misconception. Since we call them cryptocurrencies, people think that cryptography is encryption, so there are encryption in cryptocurrencies. But actually, we heavily use cryptographic hash functions, and for authentication or for transactions, we sign our transactions, so we use digital signatures. So most of the security in cryptocurrencies or blockchains come from cryptographic hash functions. So, but of course, hashing is not encryption. So the algorithms, like you heard before, SHA-1, SHA-2, or MD5 are hashing algorithms. They are not encryption algorithms. So don't forget that. So cryptographic hash functions are used to provide immutability in a blockchain, and digital signatures are used to prove ownership of digital assets in a blockchain. So this is how you make the transactions. Of course, as I mentioned before, many other cryptographic topics are started to be used in blockchains. Some of them are zero-knowledge protocols, post-quantum cryptography, lightweight cryptography, and so on. And we will talk about them in the future. So before talking about the definition of a hash function, let me give you a few examples where a hash function might be useful. So think about the situation. A forensic investigator would like to have a very small digital fingerprint of every storage device at a crime scene to detect if any modification to these devices happen in the future. So think about it in this way. You find a 1 terabyte hard drive at the crime scene. So you have to prove that during the investigation, the contents of the drive hasn't changed, okay? By malicious attempts or by other means. So you have to prove that it hasn't changed. So it will be nice to, have a function that provides a very small fingerprint or hash of it. So for a 1 terabyte, just imagine you are just producing 32 bytes, which you can write on a piece of paper. And if a single bit changes in that 1 terabyte hard drive, the hash will change. So you will prove that the integrity is broken. So this is where hash functions are always used. So forensic investigators have to take the hash of every digital storage they found at a crime scene. So another use case might be as follows. You want to find all duplicate files in your disk. So there are some softwares for this, but most of the time what they do is to check the file name, if they're identical, or the sizes of the files are identical and so on. But just to check the contents of these files, it would be nice to have, list of all of the hashes of these files and then sort them. This way you can find the duplicate files in your disk. So another use case for hash functions, millions of users upload the same file to cloud, but cloud provider wants to store only a single copy, right? And therefore limit the upload of the same file to one to save the bandwidth. So this is actually how cloud works. So assume that there's a popular image on the internet, so I put it on my Dropbox. So 5 seconds later, you also put the same file on your Dropbox. Actually, Dropbox just compares the hashes of these files and say that, okay, I already have this file, don't upload it to me. So this is why actually clouds work. And this is why they don't like encryption. So because if we encrypt the same file with different key, the output will be different. So they will have to store all of them. Another use case is as follows. An intelligence agency wants to give a list of illegal files to forensic investigators without sharing the files themselves. Because, these are illegal files, but you don't want to share them. You simply share a small fingerprint of all of these files. So when the investigator wants to check if a disk contains any illegal files, so they just compare it with this list. They take it from the agency. So as you can see, hash functions can be used in many different ways because the idea is that it produces a very small fingerprint for an input, And if input changes, the fingerprint also changes. So this way you can check the integrity if it is broken or not. So if the file is modified or not. Okay. So in the hash function, for blockchains, hash functions are used for many cases like address derivation, securing the block header, securing the block data, creating unique identifiers, creating cryptographic puzzles, and so on. So in order to understand all of this, we have to define what a hash function is and why it is secure and provides these properties. Okay, so let's start with the basic simple definition. A function h is a keyless algorithm that takes a variable length input x and returns an output y of fixed length n. This n is really short. Nowadays it is 256 bits. If you convert it into bytes, it is 32 bytes, and we call it the message digest length. Okay, so it is as simple as that. You have a function, it takes an input size is variable. It can be as small as a single bit, but it can be as large as 100 terabytes. Regardless of the input size, the output size is fixed, like 256 bits, and it is a deterministic algorithm. If you provide the same input, it provides the same output. Okay, no randomization is involved. So this is the definition of a hash function, but for cryptographic hash functions, I request more properties. And these three following properties are needed to have a cryptographic hash function. So we expect a cryptographic hash function to satisfy the following properties: Preimage resistance, second Preimage resistance, and collision resistance. So I will explain all of them, but regarding the output y, we also want a hash function to behave like a random function. So the output should appear like a random string of bits. Okay, this is important for mining puzzles actually. But first, let's focus on these three properties one by one. We start with Preimage resistance. So given an output y, it should be computationally infeasible to find any input x such that hx equals to y. So you know the algorithm h, the function hash function, you know the output, but by knowing the output, it should be hard to go back. So this is why we sometimes call hash functions a one-way function, because one way it is easy to compute. When you provide the input, it is easy to calculate the output. But if you know the output but not the input, it should be hard to invert. So we say it's computationally infeasible. But a generic attack actually would require around 2 to the n operations. So n is the size of y in terms of bits. So statistically speaking, if you take random inputs, 2 to the n many random inputs, your expected value is 1. I mean, if you provide 2 to the n different input to this function h, most probably you will hit this y value at some point. Okay, so a generic attack requires 2 to the n operations. This is how you choose the size of n actually. If you choose n very small, like 40 bits, we can perform 2 to the 4th operations very fast way using CPUs or GPUs and obtain this preimage. So,
Hocam bir şey sorabilir miyim?
Sure, but you can also ask at the end, but because I'm recording, but if you want, go ahead.
Sonda da sorabilirim o zaman hocam. Bölmeyeyim.
Choice is yours. All right, so let me give an example how we can use it. So in a password file, in the 1990s, what people did as follows. On the internet, we created accounts when we join a forum or a shopping site, and we created the username and the password. What people did was that to store them in a database like this as a plain text. But what happens next is that all of these databases leaked, and people's username and passwords also leaked. This is why many websites actually were shut down in the beginning of 2000s. Okay. In order to avoid this problem, what you can do is as follows. Instead of storing the user's password, just store the hash of the password. So instead of X, store Y. Because when the database leaks, the malicious people will obtain all of the Y values, so hash of your password, but it will be hard for them to obtain the password from them. So storing this is not a problem when logging to the internet, logging to this website, because when you log in, You actually provide your username and password. The server calculates the hash of the password you provide and compares it with the hash in the database. So if they match, you successfully log into the web page. So this is sufficient to verify a password. An attacker that captures the password file or the database has to find a preimage. But of course, I'm explaining here in the basic definition. This is not how we store passwords. Actually, in practice, we also concatenate a random value to the end of this password that we call salt. And instead of calculating hash here and writing it to the database, we do not stop there. Take this output and put it inside the hash function as a new input and repeat this process thousands of times and obtain the hash value at the end and put that in the database to slow down the attacker's brute force attacks. Okay. But as you can see, this is very useful in, securing passwords. So let's move on to the second property that we want. So it is called the second Preimage resistance. Given an output y and an input x1 such that hx1 equals to y, it should be computationally infeasible to find any other input x2 such that hx2 equals to y. So this time you have an input, you have the output, which is easy to calculate if you already know the input. But now you are trying to find another input which is different than x1, but also provides the same output. So this has to happen. You have to understand that because, for instance, think about SHA-256. In that hash function, we limit the size of y to 256 bits, right? But we never limited the input size. So input size is almost infinite, and the output size is 2 to the 256 different values. So of course, many different inputs will lead to the same output. So this is inevitable. But what we want it to be computationally infeasible. So a generic attack, a brute force attack where you try random x2 values actually requires 2 to the n operations. Okay. So this is also important. And you can, for instance, do the following. You can store the hashes of your files or the drivers you put on the web or so on, just to check if somebody modifies them. So if the attacker modifies the file, for instance, if a virus modifies a file on your computer, for example, put a malicious code inside them, and can still obtain the same hash value, then the attacker can fool you, right? Because you think that it is the original file, but actually it has a virus inside it. I will give more examples about this in the future. But let's move on to the third and the final property that we want. So what we want that it should be computationally infeasible for a hash function to find two inputs x1 and x2 such that hx1 equals to hx2, which equals to some value y. So at this point, we have to stop and ask what is the difference between this one and the previous one. In the previous one, x1 was fixed. Okay, so there was the x1, y, and you were trying to find x2. Now I'm giving you more freedom. I'm only giving you the hash function h and asking you to find just any two inputs that give the same output. So as you can see, since you have more freedom here, a generic attack is actually easier here. A generic attack will require around 2 to the n over 2 operations due to the birthday paradox, which I will explain in the next slide. Okay. So why this is important? Assume that a hacker prepares two versions of a software driver for an operating system, where x1 is the correct one and x2 contains a backdoor that allows access to the machine. So you are the hacker. You prepare two files. You have control on both of these files. And x1 doesn't have a malicious code in it. x2 has a malicious code in it. And if their hashes are the same, then you can actually break many systems, because hacker sends x1 to the operating system company for inspection, for instance, Microsoft. Microsoft checks this driver, executable file, and finds no problem in it, and signs the hash of this file. When we digitally sign something, we always sign the hash of it, because if you sign the whole message, for instance, think about drivers nowadays, NVIDIA drivers exceeded 1 GB at some point. If you sign 1 GB file, it will be a huge signature, which will be very hard to use it in practice. But when you take the hash of it, it is very small. Then Microsoft signs it, and with the signature, when you want to install it, operating system checks if it is signed by the operating system and says that, okay, this file is secure. But the problem is that since hash of x1 and x2 are identical, hacker now puts the x2 on the web. And when you download it and try to install it on your operating system will think that this is a secure file because it is signed by the operating system itself. Okay, so this is one way of actually spreading virus, and Flame malware actually did something like this using MD5 collisions. Okay. All right, let's return to birthday paradox. Question is, this is to understand why finding collisions requires 2 to the n/2 operations. Okay, so compared to others require 2 to the n operations. Now we have a square root on top of this value. So we want to understand why this is the case. So let's define what the birthday paradox is. So question is, how many people need to be in a room before it is more likely than not at least 2 people share a birthday? So imagine a room, 1 person enters. Of course, since there's nobody else, they don't have a collision. But when the second person enters, it is possible that they share the same birthday, but it is highly unlikely, right? Because there are 365 days in a year, so you should be very lucky to obtain 2 people and they have shared the same birthday. But when more people start coming in, at some point, probability of having 2 people with the same birthday is more than 50%, okay? So with probability more than 1/2. So the question is, at which point, how many person is in the room, then we have the probability is more than 1/2. So we call this a paradox because when we ask this question, people think that maybe 100 or 200 people should be in the room, but the answer is less than that. I think it should be 23, yes. So it is very small number compared to people's expectations, and this is why we call it a paradox. So let me explain why the answer is 23 and how it is used for the collisions in hash functions. So consider the probability that nobody shares a birthday. So let's calculate this. The first person in the room has a birthday on a given day. So with probability 1, they doesn't share their birthday, right? Because there's only 1 people. To avoid a match, the second person is left with 364 days to have a birthday. So when you have 2 people, the probability of they don't share a birthday is 1 times this. The third person now has only 363 days remain. So if you have 3 people, the probability that they don't share a birthday is the multiplication of these 3 values. So as you can see, this is how it goes. So if there are 3 people in the room, the probability is as follows. So this is the probability that they don't share a birthday. So if you put 1 minus this value, okay, 1 minus this value, then it will be the probability that they share a birthday. At least there is 1 match, okay? So the question is, when this probability x is 1/2, okay? So you can just put t equals to 1, 2, 3, and so on, and you can find that at some point this exceeds 1/2. But let me give you the solution. When you take t equals to 23, the probability becomes 0.507. And if t increases, this increases in a really fast way. So there are, for instance, 30 people in the room. You can play this game, ask everybody's birthday, and write them on the board. At some point, you will see that 2 people actually share the birthday, okay? But if you generalize this, for instance, in our scenario, in this problem, the year has a 365 days. But in our collision problem, we had a hash function with n-bit output. So we had 2 to the n different days for people to have the same birthday, let's say. So for the more general case where we have t people and n possible birthdays, it can be shown that p equals to 1 minus e to the minus t square over 2n, which is not that hard to calculate, by the way. It is from basic calculus. So when there are n possibilities, after making approximately t equals the square root of n choices, we have a collision with probability more than 1/2. So this is why, this is due to the square root, we say that a collision resistance actually requires 2 to the n/2 operations, okay? This is why it is easier to find collisions, and this is why actually we use algorithms like SHA-256, because if you divide 256 by 2, you obtain 128 bits. So 2 to the 128 possibilities, we call this 128-bit security, which is the minimum security we allow in 2023, but this is the thing that we do since 2010, I guess. All right, anything less than 128-bit security is not acceptable for me. Okay, so final slide. We call these hash functions Swiss Army knife of cryptography, because in cryptography, you can see hash functions everywhere. So hash functions have many uses in cryptography and are considered the Swiss Army knife of cryptography. Some of them are digital signatures, message authentication codes, pseudo-random number generators, key derivation functions, and so on and so forth. So you will see hash functions many times in different algorithms, but also outside of cryptography, you can use hash functions for many purposes.